This set of notes is about other characteristics of gases. Second characteristics that we want to talk about today are effusion and diffusion. If you remember from last unit when we talked about Maxwell-Boltzmann equations, you might remember the temperature-speed relationship and the molar mass-speed relationship. Take a moment, put those back into your brain. If you need help remembering them, down here on the bottom. But you'll remember then that as temperature increases, the average speed of particles increases. And as the molar mass of different substances is bigger, the speed decreases. Okay? These two ideas, these two relationships that we learned about back when we talked about Maxwell-Boltzmann, leads to two particular gas behaviors. One called effusion and one called diffusion. Effusion is simply the escape of a molecule through a tiny hole in an evacuated space. So imagine that you take all your gas, you put it in a container, and then you have a membrane or something in there that has a small hole in it. Okay, in that you could create that small hole, and as particles go through that hole, they go into an evacuated space that has no particles. That process of moving from higher density to lower density is called effusion. Diffusion is a similar process, but it's on a larger scale in 3 dimensions. So rather than just going through a single hole in one direction, diffusion is the spread of one substance throughout a space or throughout a second substance. So here it is. You have particles. They start moving and spreading through an entire container. Maybe you started with them all in one spot, and again, they spread through the entire container. That is diffusion. All right. So when we think about these, as I said, they're related to the molar masses and the temperature, right? Factors that affect them. So back last unit, we learned about root mean square speed, and we can abbreviate that with a U, okay? And there's actually a way we can calculate that. We're never going to have to calculate that, but if you'll notice here, what's involved? Well, universal gas constant, temperature, and molar mass. This makes sense based on what we just talked about in terms of Maxwell-Boltzmann. So again, changing the temperature is going to affect diffusion and effusion. Changing the molar mass is going to change them as well. So the question is why? Well, simply if you can get particles moving faster rather than slower, they're going to be able to move through a space much more quickly. And so as a result of that, you can probably see already, increasing the temperature is going to increase diffusion and effusion. Decreasing the molar mass is going to affect the diffusion and the effusion and make it go faster. So for effusion, we actually have a calculation that we can use for this when we refer to molar mass. So assuming we're at the same temperature, speed is inversely proportional to molar mass, right? Greater molar mass, less speed. So proportionally, if you want to compare how fast two substances are going to diffuse, substance A and substance B, you can figure out what the proportionality of the differences in their effusion rates are by taking the molar mass of B, dividing it by the molar mass of A, and taking the square root of that. This idea explains why, if you had two balloons, one filled with argon, which is heavier than air, or more dense, helium, which is less dense than air, so there they are sitting there, and you put a single, very tiny hole in either one of them, what you're going to notice is that over time, the helium gas balloon is going to deflate faster than the argon. Why? Well, again, helium, lower mass, so the particles are going to move faster, and so that means that they'll effuse through any tiny holes in the balloon much faster than the argon ones will. When we talk about diffusion, the idea is the same, right? The instantaneous speed ideas are the same, so you can go ahead and have particles that are moving faster. However, as a particle starts moving through the space, it'll bounce into other particles, changing its direction. And so as a result of that, what you end up with is a path through the thing that might be very, very convoluted. And so that will lengthen times for diffusion that we don't see in effusion. So as a result of that, because it's so random, there's no easy calculation to figure out how fast diffusion rates would be. The last characteristic that we want to talk about is vapor pressure, okay? So it says at any temperature, some molecules in a liquid will have enough energy to break free and become gas. So if you think about your Maxwell-Boltzmann distribution, at some point, particles have enough average kinetic energy that they no longer are part of the liquid, but they are part of the gas. That happens. Same thing can also happen in a solid. There are, of course, in a distribution of a solid, there are going to be some particles way out here at the end that have enough energy that they can go and break free and become gases. Obviously, that's going to be a lot less in a solid than it is in a liquid, but nonetheless, it happens. So if this process is happening in a closed container, the molecules that escape are going to start exerting pressure, right, up in here. So as we get more particles up here, they'll start creating pressure. As more particles escape, the pressure that they exert increases even more. Okay. At some point, you get to a state where enough liquid particles have evaporated and turned into gas, and enough vapor particles now that are on the slow end of their spectrum are condensing that happens at the same rate. This happens in a closed container only, because in an open container, these vapor particles would go out into space and your concentration would always be higher in your liquid. So if it's in a closed container, you get to a state where the number of particles turning into a liquid at any one point in time is the same as the number of particles turning into a gas at any one point in time. We refer to that as equilibrium, which we'll talk about a lot more later on. But at that point in time, you'll have a pretty constant number of gas particles up here. And since you have a pretty constant gas number of particles, the pressure will stabilize at that level. That pressure is called the vapor pressure. There are several factors that affect the vapor pressure of a substance. Okay, first factor that affects it is the temperature. Obviously, if you have an increase in temperature, your curve shifts to the right, and the fraction of molecules that have enough energy to break free increases. Okay, which means that you're going to have more gas particles on average in the space above the liquid, and so as a result of that, if we have more gas particles, we know that an increase in N equals an increase in P, so more gas particles is going to create more vapor pressure. So an increase in temperature increases the vapor pressure. Second thing that's going to affect is IMFs, which is going to have a higher pressure, water or ethanol. Think about it for a moment. We know that water has extensive hydrogen bonding in it, and so therefore the IMFs of it are going to be greater. Now you can imagine that if the IMFs are greater, that means it's going to be harder for that substance to evaporate and generate gas particles. So as a result, weaker IMFs means more particles can break free, so weaker IMFs equal more vapor pressure. Greater IMFs equal greater vapor pressure. So that's it. IMFs and temperature are about the only things that affect the vapor pressure of a substance. Okay. Liquids with a high vapor pressure evaporate easily, or probably the better way of saying it is liquids that evaporate easily create a high vapor pressure. If that's the case, we refer to them as volatile liquids. Why? Because they will readily evaporate and create a high vapor pressure. Now, vapor pressure is important for a bunch of different reasons because it tells us about rates of evaporation, but it also tells us about boiling. So we're going to watch a video here that has to do with the boiling point and how vapor pressure is related to that.
We know that boiling is strongly influenced by atmospheric pressure. Pulled down by gravity, the air above us creates pressure, and that makes it difficult for bubbles to form and boiling to take place. We can think of atmospheric pressure as the collisions of air molecules against the surface of the water. That's the pressure. The more collisions, the greater the pressure. But water molecules can create pressure when they leave the liquid. As these faster moving water molecules escape, they collide with the molecules of air. This creates pressure, and we call it vapor pressure. In a way, the water molecules are pushing or colliding against the air molecules. This reduces the amount of pressure felt by the water. Back to boiling. Textbooks often state that when the vapor pressure equals the atmospheric pressure, boiling takes place. This is called the boiling point. Think of it this way. Atmospheric pressure pushes down, and that makes it difficult for the water molecules to spread out and form a bubble. But when the vapor pressure increases, molecules from the liquid escape, and they push against the air molecules and effectively reduce some of the pressure. This makes it easier for the liquid molecules to spread out, form a gas, and to rise to the surface. That's boiling. We can make boiling happen by either increasing the vapor pressure or decreasing the atmospheric pressure. Either way, once the vapor pressure and the atmospheric pressure are equal, we've reached the boiling point, and boiling can begin. One last thing. Different substances have different vapor pressures, and therefore they have different boiling points. This has to do with how strongly the molecules are attracted to each other in the liquid. The more strongly they're attracted, the less the vapor pressure, and it's more difficult to boil. Therefore, the higher the boiling point.
All right, so there's the basic explanation. So again, in terms of vapor pressure and boiling, the higher the vapor pressure, the more easily it is to boil something. So as it is stated in the video, the boiling point of a liquid is the pressure at which its vapor pressure equals atmospheric pressure. Okay. The normal boiling point is the temperature at which its vapor pressure is 1 atmosphere. So basically the normal boiling point is the boiling point at standard pressure. Okay. So the last piece of this that we need to talk just a little bit about is phase diagrams, because we've just learned that external pressure helps us dictate when something is going to change state. We also know that temperature is going to dictate that as well, because that changes the vapor pressure. So as a result of that, we can create phase diagrams, which is essentially a graph of what state of matter is a substance in at different combinations of temperatures and pressures. This is in your book, and I'm going to have you go ahead and just skim through that so you can understand what it's about. But understanding that different temperature and pressure combinations create different state of matter changes. Okay, so for example, when we talk about sublimation or deposition, going straight from a solid to a gas, this is a state where the temperature and the pressure conditions are such that a solid can create enough vapor pressure to turn directly into a gas. Okay, if we get different conditions, that won't happen with the solid, and we'll have to go through a transition where we go from liquid first before we get to solid. There's other pieces of this that you can read about and understand a little bit more about, but this idea of phase diagram is not on the AP test. It's not tested. They assume that it's something that you've gotten in a previous chemistry course. So just want to pull it out there because it is related to the topic that we're talking about today, and I would like you to skim a little bit of the materials having to do with that.